Now, the kind of contact interfaces have already been discussed. However, there can also be different types of contact bodies which are involved in a particular analysis, and that is something that can be identified depending upon the problem that you're looking at. So you can have in one case you can have a flexible contact. And by flexible contact, I mean there are two bodies that are quite similar in stiffness and both can deform. So the two characteristics we are looking for are that both of them are deformable bodies and both of them have similar stiffnesses. The second case is a flexible rigid contact, which means you have one body which is deformable while the other body is rigid, which means the stiffness are very different. So we can say that stiffness of the second body is significantly greater than stiffness of the first body. Therefore, the second body can hardly deform or can be considered to be rigid. For example, if you have a rubber ball which is hit against a steel wall. Now, why can't we use this object, so the flexible rigid contact, in a flexible condition? The reason why we don't do it, or we don't use the same definition for both flexible and flexible rigid contact, is that if you look at the stiffness matrix for a certain system, then if we have two different objects which will have flexible and rigid bodies, then you would see that you have a certain stiffness matrix which would have very high stiffness for one of the bodies, however very low stiffness for another body. And this makes the matrix ill-conditioned. And this is not a situation that you would like to have for solving a problem. So you need enough to model contacting surface only for the second body. That's all that is required. You just need a surface, and you know that it has very high stiffness, so it's almost like a rigid domain, but you don't need to have any stiffness or K properties determined or defined for this body. Now you can also have friction in the interface. You can have flexible contact, you can have flexible rigid contact, but you can also have friction within the interface, which makes the contact analysis to be path dependent. That means if I have, for example, a tire which is rolling on the road, you have a tire which is rolling on the road over here, then if you have a certain friction which is defined, then the contact analysis will also become path dependent on how the load is applied. So this is of course different kinds of examples that you can use in this case, whether you have flow of a certain liquid or molten substance inside a injection molding tube with a piston, and this will have a different contact definition than the one which is explained over here for a tire. But the idea is that if you have friction, then it becomes path dependent problem. So now we know that there is a certain way by which the contact formulation happens, and you can have contact between deformable bodies, but also between deformable and rigid bodies. Of course, the contact definition between deformable rigid body becomes easier because one of them is considered to be infinitely rigid or high stiffness. So the solution is much simpler. Now you have flexible contact which can also have friction involved, or both of them can have friction involved, which adds a certain extra problem. Now the way the contact is always applied in an analysis is not just by searching and then applying a certain force, but there also have to be some rules that are set up on which body behaves as a master and which body behaves as a slave. So this is a classical way of describing a contact analysis, and that requires the definition of master-slave surfaces. or master-slave bodies. Now, theoretically, there is no need to distinguish between two bodies. However, for numerical purposes, we have to make the distinction. That is why we have to call one of the bodies a master and the other one a slave. So I'm going to say this is only a numerical consideration. In the contact condition, we specify or we stress that the slave body cannot penetrate the master. This is a standard rule that is applied. The master body can penetrate into the slave body. Physically, of course, it's not possible, but numerically, it has to be enforced. So if we pick up the same example that we had before of a surface with this hemispherical or just a part, the surface over here, and if we consider this to be the master and this part to be the slave, and I have as usual defined some nodes on the surface and also for the slave, then in principle the master nodes over here can penetrate inside the slave body. Physically, it's not possible because this is of course certain mass, but as I said before, if your increment sizes are too large or not properly described, then it could happen that we skip that and numerically there is a penetration because the contact surfaces are not identified at all. So the contact condition therefore is described between the slave and the master just by using the gap function that we had discussed before. If you had the gap function, which I can write over here as a value of x or the distance minus a certain known value of x1, so at a certain level over here, so let's say you have a distance x and this is x1 with the normal vector, or let's say the basis function of a normal, then the gap is greater than equal to 0 does not have any contact. But if your gap function becomes less than 0, then you have a contact condition that is activated. But this we have seen before. So the slave and the master surfaces or objects have to be selected. It is not something that comes as a inbuilt function for the program. So a slave, as we have already decided, cannot penetrate the master, but the master can penetrate the slave. There is not much difference in a fine mesh, but the results can be quite different in a coarse mesh, right? So if I have shown you one example of corresponding node properties that are present over here. If in another case I had similar object here, and here in the master I had many nodes which are present on the surface, but in the slave I have nodes that are present quite far away from each other, then all these nodes here can easily penetrate inside the slave surface. So this is master, this is slave, because there are not enough nodes that are going to be able to supply a reaction load to create the contact. So when there is a fine mesh or equally fine mesh, let's say on both of them, it doesn't make much of a difference. But if you have such opposing meshes in both cases, then there is a problem. So there are some simple rules that have been defined for how to choose a master and a slave. The rule number 1 is that if you have a rigid body, so you have a rigid surface, the rigid surface always becomes the master, right? Because you don't want the slave to enter the master. Secondly, if you have a convex surface, then the convex surface should be made a slave. But what if the convex surface is also a rigid surface? Yeah, so you need to make the correct decisions or make a good trade-off as to which one should be what. And finally, if you have a surface with a fine mesh, then that surface should be made into a slave surface, because you are then imposing conditions that the master cannot penetrate the slave because it has enough reaction forces that can be generated at each of these nodes to become contact forces. Now, we need to always make sure that we define master-slave pairs in such a way that penetration does not happen. Some of the programs have inbuilt functions that disallow this penetration. So you can use all kinds of tolerances to make sure that your surface-to-surface definition does not allow any penetration, whether it's during analysis or just at the first step of analysis.